So why do we want to work with single molecules, and what do we get out of it? Well, the single molecule experiments can give you unequivocal information about how enzymes work, and they can give you new insights into enzyme mechanisms. So if you can watch a single protein, let's say bind ATP and go through some conformational change, by just being able to measure that distance and that force, you get a measurement which is unequivocal, as it were. And I guess the best demonstration of this would be the F1 ATPase. And I don't know if any of you have seen this experiment where the enzyme in your mitochondria, which produces ATP, called the F1 ATP synthase, by attaching an actin filament onto the end of that molecule, you could see it rotating on the light microscope. And it's just such an unequivocal demonstration that protein works as a rotary enzyme, because you just see it before your very eyes. I mean, there had been bulk experiments to show that before, but there's nothing like actually seeing it. Seeing is believing, and seeing a protein actually rotate and go around in circles, it's just unequivocal. So you can also look at the sequential steps that make up a biochemical pathway. So for many bits of biochemistry, you'll have a series of discrete states as you move through a pathway. I'm going to come to this in a minute for the muscle system. But the idea that you can follow an enzyme binding substrate, converting substrate into product, and then releasing product as 3 or 4 different states as it goes through a pathway. If you can visualize that somehow directly, then you can establish the order in which those reactions occur. And that otherwise is quite difficult to do through a bulk biochemical experiment. So you can look at what we call the chemical trajectory, how an enzyme works and processes a substrate and turns it into a product in a series of steps. The other advantage is that because you're working with individual molecules and you're collecting data from a whole field of individual molecules doing their chemistry, you can just watch each molecule independently, and you don't have to synchronize the population. And what I mean by that is if you have, let's say you wanted to look at the turnover of ATP by an ATPase, if you wanted to look at the rate at which that reaction occurred, you'd need to synchronize. If you have a cuvette of molecules, you need to synchronize them in some way. So you starve them with ATP, give them ATP, and then watch how the ATP gets turned into ADP with time. But essentially, you've done it by synchronizing the whole population. So they all start in one state, and they move through their pathway gradually with time. And you look at the evolution of that pathway. With a single molecule experiment, you don't have to do that because the individual molecules are being given their ATP, delivered one molecule at a time. And if you can look at this molecule here and this molecule here, then you can put it back, you can assemble that in the computer. So you just keep all the information from each individual molecule separately, and then you reassemble it in the computer to produce your transient in time for the population. So you don't need to synchronize them, or come up with clever ways to biochemical methods. And then finally, single molecule data. As I said, you can reassemble the data in different ways. So if you record it from a single molecule, you can then treat that data set in a whole variety of different ways in the computer. And you can specifically look for, for instance, for heterogeneity in behavior. So if you believe that some of your molecules work fast and some of your molecules work slow for some reason, you can test that specifically by looking at the individual molecules and seeing, let's say, if they divide into 2 populations, fast ones and slow ones. And if you were measuring them in bulk, because it would be a mixture, you'd never be able to get that information. Okay. So the mother of all single molecule experiments was in fact the work done on nerve and the nerve conduction method. And the first technique that was used was developed by Nair and Sackler in 1976. So around the time actually that the optical tweezers were being developed, these guys had developed an electrical system for measuring the current that flows through a single ion channel. And that involved taking a patch of membrane, which on average had, let's say, 1 or maybe 2 ion channels embedded in it. And when the ion channel opens, by having a very sensitive amplifier, you could follow the current as the ions go through the channel. And the secret to the whole thing was getting the connection between this pipette tip and the membrane to have a very high resistance. That's rather like using optical tweezers to have a very high stiffness, so you're you're trying to reduce the amount of, here you're reducing the amount of electrical noise. With the optical tweezers, you're trying to reduce the amount of mechanical noise. So if you have a poor connection, you have a noisy signal. And if you have a good connection, you have a very clean signal. And the amplitude here is of the order of a few picoamps. And the reason this system works relatively straightforwardly, I've never done a patch blend experiment, but the signals here are fairly large because when the channel opens, there's about 6,000 ions on average, or you can find 10,000 ions go through the channel. So you've got huge amplification of the signal. Although the protein has undergone a single conformation change, one protein changing shape, the actual signal is derived from the flux of up to like 10,000 ions going through the channel. So this has built-in gains because the flux of that many ions gives you quite a big electrical signal. And the reason I say that is when you come to do, and the same goes for optical methods. So if you're looking at the properties of a single fluorophore can emit millions of photons. So again, you have built-in gains. You hit your fluorophore with a laser, and it throws out millions of photons for you to measure. When you do mechanical experiments, you have essentially no built-in gain. So in terms of athletics, this has a difficulty of 6.6. It's very difficult to make these measurements because the signal that you're measuring just derives simply from one ATP molecule. So it's only that 100 piconewton nanometers worth of energy, rather than 10,000 times the energy from an ion going across the membrane. Okay, so there are three different methods, broadly, for making single molecule mechanical measurements. So optical tweezers, which of course, sorry, this is just getting, I think I need to go back to, I'm going to switch to manual. Okay, so there are three different methods. So there's optical tweezers, magnetic tweezers, and atomic force microscopy. And these first two techniques, optical tweezers and magnetic tweezers, work in what you might call the low force regime. They're producing forces in the order of 1 to 10 piconewtons. And the atomic force microscope is better in a sort of slightly higher force regime. So atomic force microscopy is used extensively for looking at protein unfolding, for instance, which requires much larger forces. Whereas these two methods, magnetic and optical tweezers, have been used for measuring the properties of individual protein-DNA interactions and protein-protein interactions. And both of these allow you to make measurements in 3 dimensions and also apply twist. And I think you heard from Professor Ormus last week about using optical tweezers to produce twist, for instance. So let's now see what we're going to get out of these measurements. So I mentioned it's just a bit of the biochemistry. So what are we actually going to measure with our optical tweezer? So if you have a biochemical system that you want to know more about, let's say the simplest thing that we can think of, A goes to B. This might be ATP goes to ADP and phosphate, or it might be whatever. Some chemical goes from one state to another state. And we have 2 rate constants which govern those transitions, a forward rate and a reverse rate. And that's often drawn as a transition state diagram where you might have state A represented at a high energy level, state B at a lower energy level. And we can see from the way this transition state diagram is drawn that A is going to, on average, A will tend to get converted to B, and the equilibrium will be strongly favoured in the state B. And in these transition state diagrams, the rate at which the chemical A transitions to B is proportional to this barrier height, and similarly for B to A is proportional to this barrier height. And there's a little bit of mathematics here which relates those rate constants to these energies and to the equilibrium constant, K, which is the ratio of these two rate constants, which actually is the total energy difference, delta E. Okay, so I mean that's sort of basic transition state theory for a simple kinetic scheme. Well, let's see what happens when you do your experiment. So we're going to look at that reaction now. And what we've done in this is a simulated experiment. So we've got time along this axis. Let's now imagine that we have our chemical, and it's all in state A initially. So it's representing state A is down here at 0. And then we allow the reaction to occur. So suddenly we've added some, let's say, ATP, and it's all going to then flux over towards state B would be 1 up on this axis. So it fluxes across, and then it reaches an equilibrium, which is, in this case, something around 0.7. So the A has gone, and at this equilibrium, you can see that it's noisy because it's fluctuating. A goes to B, B goes to A, and the molecules are individually fluxing backwards and forwards between these two states. And what do we get from such an experiment? The answer is, so this is a common thing that biochemists will do. Let's say, if you have an optical signal, you can put it into a cuvette. You can measure, let's say, the optical absorbance. You'll have some sort of signal that you can measure. And you'll see that signal increase with a particular rate constant, and that observed rate constant is the sum of the forward and reverse rate constants. And the final amplitude that you reach here is the equilibrium constant. And so just by doing this one simple, what we call mixing experiment, where you just mix the two things together, and you look at it in your spectrophotometer, you can measure the two rate constants, and you've got the equilibrium constant. So you know everything, basically, just from that one simple experiment. And as I say, why bother doing a single experiment since it's so simple? Just get a spectrophotometer and do it. Well, and what happens when you reduce the number of molecules in your cuvette? So imagine you've got your stuff in a little cuvette in your spectrophotometer, and then you dilute it 10-fold, 100-fold, 1,000-fold, 1,000,000-fold, and you get down to the point where it's almost like homeopathy. So let's just do. We can simulate that in the computer very easily. And as we reduce the number of molecules, now we've got 10 molecules, only 10 molecules bouncing around inside our cuvette. And we see the same basic property. It starts off all in state A, and we can now see it's actually got little steps here, as you can see things transitioning forwards, and then they're starting to come backwards again. They go forwards, they come backwards. And we're getting it saying, oh, there's a big excursion here. There we go. And you can see it fluctuates around 0.7. So we've got the equilibrium constant still at 0.7, and we've got an estimate of this initial rate here. But all we've done is we've made the signal worse. Okay, so by going to 10 molecules, we've gained nothing, let's see. We've just got a worse experiment. So what was the point in that? And the reason for that is that then you can get down to what we call the single molecule state. And you could say, well, now we've lost everything. Because the equilibrium constant, how do we get the equilibrium constant out of that? It's sort of 1 some of the time and 0 some of the time. So we've got no estimate of the equilibrium constant. What about the initial rate? Well, the initial rate is just represented by this initial delay here. So we've only got one molecule, we've only got one estimate of that rate. Very, very poor estimates of the rate constants and of the equilibrium constant. So somehow the information's all just disappeared and we've got nothing. And the secret is that the information now is all essentially digital, and it's all encoded now in time rather than in amplitudes. And so as we read through the data, what we find is that the individual molecule will either be in state B or in state A, and it will fluctuate between those two states, backwards and forwards, and it'll go on ad infinitum, just fluctuating backwards and forwards. And the way that we derive now the rate constants for the forward and reverse processes is to measure the time that it spends in each state. So these would be these dwell times. So this would be called dwell time analysis. And you can measure, let's say, T1, and actually 1 over T1 tells you the reverse rate constant, and 1 over T2 tells you the forward rate constant. And now, an individual pair of values gives you rather a poor estimate, but by recording over time, and recording now many thousands of these interactions, it's like recording from 1,000 molecules, if you assume that the thing's a completely homogeneous system. So we just space it out, so now we're recording in time, and we can record those transitions. We essentially get the rate constants, and we also get the unitary amplitudes. So when I say the unitary amplitudes, here I've just used 1 and 0, doesn't mean much. But let's say this was 5.3 nanometers and 0 nanometers. If I was interested in a conformational change, that would be quite an important thing to know about. So these amplitudes now are single molecule amplitudes, or whatever units that's expressed in. So the question then is, can we use optical tweezers to do that kind of measurement, to take a single molecular motor and see it transition through its ATPase cycle and convert one molecule of ATP to a little bit of force and movement, and maybe even go backwards and forwards, so we can just record endlessly from one molecule and measure exactly what the amplitudes are, how much force, how much movement it produces, how rapidly it breaks down ATP. Get all that information just by looking at one molecule, staring at it for maybe several hours, and just watching it fluctuate back and forwards. Well, to do that, we need to have a measurement system, and that's where the optical tweezers come in. So let's again go back to let's see where we're starting from. And I'm going to remind you about these molecular motors. And so the best studied molecular motor is are the proteins in your muscles. And as you know, your muscles have muscle fibers, which are the individual cells, and inside each one of those fibers are very highly ordered arrays of proteins. And the two main proteins in your muscle are actin and myosin. And actin is a long, thin, filamentous protein which stretches out along the axis of your muscle, along this way. And in between the actin filaments, you have what are called thick filaments, which are made of myosin. And the myosin thick filaments consist of a very rigid backbone, and it's sort of decorated with little sort of knobs, little lumps sticking off it. And those, if you look under higher magnification in electron microscope, this is the thick filament here. And these little projections project out from the backbone of the thick filament and then interact with the actin thin filament. So there are little cross connections between this thick filament and that thin filament. And that happens in this mid part of what's called the muscle sarcomere. And so that's where the two proteins can interact. And actually this electron micrograph here is shown in what's a state of muscle called rigor. And that's what happens. This is when you die, heaven forbid, and your muscles go rigid. The reason that your muscles go completely rigid is that the ATP has been used up because there's no ATP regeneration system going because you stop breathing. And when that happens, the myosin molecules look exactly like this, where they're all projecting out from the thick filament and all binding onto actin and making a stiff, rigid connection between the actin, the thin filaments and the thick filaments. And that means that your muscles can no longer extend and lengthen. In fact, in the relaxed state, as you are now, there's plenty of ATP in your muscle. You have about 5 millimolar ATP sloshing about inside your muscle fibers. They're turned off, and nearly all of these heads, rather than projecting out like that, are actually sort of collapsed down back onto the thick filament. And then you wouldn't actually see any of these little cross links. And the filaments then can just move past each other very, very easily. So a relaxed muscle is very easy to extend, which is just as well, because when I tighten this muscle, I want this muscle to be nice and easy to extend. Okay, so that's muscle. And this is so bulk experiments have shown us this is sort of the way that it works. The two sets of filaments slide past each other, and in terms of the magic that's going on, is we want to understand how these little heads of the myosin somehow grab hold of the actin and pull it this way, and these are the ones that pull the actin that way and make the two sets of filaments slide past each other. We know muscle uses up ATP, so we know that's the source of fuel, but we don't really know how the fuel is taken by one of those little bits of protein and then turned into force of movement. How on earth does that work? Well, first of all, the chemistry, and it is one of these chemical schemes, and indeed most of these single molecule experiments are all about trying to understand some sort of bit of biochemistry where you have multiple states. And we know that when myosin breaks down ATP, it undergoes a typical pathway for an enzyme, which is for the enzyme to bind the substrate, ATP, that's the first step, so it has to actually get into the protein. Then the protein does something, and it hydrolyzes the terminal phosphate. And so now they're still inside the protein, but now you've got ADP and phosphate, and that oxygen bond has been cleaved between the two of them, between the gamma phosphate and the beta phosphate. And then you have to release the product. So we have to, in fact, first of all you let the phosphate out, that can get out of the molecule. Now we've just got ADP in there, and then the ADP gets thrown out. And now we've regenerated an empty enzyme, and that can come back to the beginning by another ATP. And that's why it's a cyclical reaction, because the enzyme itself is not used up. But what you do is you use up the substrate and convert it into the product. So we've got a nice little system. Myosin will happily take ATP and convert it to ADP and phosphate. It's chewing up ATP. But it's not doing any work at the moment. All it's doing is because the solution will actually get hot, but it's all completely futile. So this is where the actin comes in. Decorate the whole thing. And when you add actin, if you have your, as I say, this bulk cuvette of myosin, and you add actin in there, now the pathway looks rather different in that remember I said that the two proteins form a very tight link together in the absence of ATP. So this is your rigor state. It's called AN, because it's actin and myosin forming a tight bond together. So when there's no ATP in the myosin molecule, the two things stick together. Then you add ATP and the two things fall apart. This is your relaxed muscle, so the two proteins no longer interact. And they have either ATP or ADP and phosphate in the catalytic site of the myosin molecule. And then the release of the product, the phosphate can only get out when myosin rebinds onto actin. So the phosphate, as it were, is trapped inside the molecule. It's only when it binds onto actin that somehow opens up the catalytic site so the phosphate can get out through a little hole. And so that is actually, as it were, the step that's regulating this ability to do work. So this release of phosphate and then the release of ADP only occurs when the two proteins are bound. And it's this region of the pathway where we think, or we've thought for a long time, that the protein maybe changes shape, and that shape change might produce a little bit of movement. So now on this pathway we've got something like an understanding between the chemistry and how that chemistry might couple into mechanics. Well, that's great, but it's still just a scheme. How do we actually prove this scheme is correct? We need to do some sort of experiment that's going to measure this little movement and any of these other states that you can get hold of. Because to put it as, in fact, the physicists really preferred this. Most physicists prefer this sort of scheme. Anything for me? No. I was doing it here, it's not doing it there. It's a fantastic video. So a thermal ratchet. I don't know. Actually, we turn off the display here. And sometimes comes out everywhere else. You take it out. In a way, these movies don't really matter. I mean, but there are two. How the actual how the force of movement are generated. It can either be produced by a thermal ratchet, where this myosin molecule would fluctuate back and forth, bind actin, and then pull the actin back because of the extension of this spring, which would be driven essentially by ratcheting or the thermal motions by allowing it only to bind when this spring is extended, or what we call the power stroke model, where the myosin molecule would bind and then undergo a conformational change. And these are subtle things, but they're the sort of things that we want to understand. So we need to have a system. In order to study single molecules, it's not just as simple as just having a cuvette and you just dilute down. You've got to have some way of capturing the molecules and positioning them in some way that you can actually record from them. Otherwise, they'll just diffuse out of your observation volume so rapidly that you'll just never be able to follow the properties of a single molecule. Remember, I said what we want to do is sit on top of a single molecule and just watch it for hours, fluctuating backwards and forwards. If it's in free solution, you'd have to be chasing around all over the place and trying to follow it. There's no way you can do that. So you need some way to immobilize the proteins so that you can make these repeated observations. And this is enabled, well, in the same way that the patch pipette, where you held that little piece of membrane, you've immobilized just one channel into the end of your patch pipette, and it's just trapped in there. And that's why you can sit on it. In this experiment, the key step was developing what's called an in vitro motility assay, where we could immobilize myosin molecules So this is recorded using a fluorescence light microscope. So you label the actin filaments with a dye molecule, usually rhodamine, which is a nice bright fluorescent dye. And actin actually will bind rhodamine. Every single actin monomer will bind a rhodamine dye. So you get quite a bright signal from a single actin filament. I say bright. This is an image intensified camera. That's why it's dotty. In fact, your eyes have to be fully dark adapted. When you look down the light microscope, you see nothing initially. But then if you're in a darkened room, you can just see these little tiny red threads under the light microscope. And the observation is these things are moving. They're obviously moving in a directed manner. This isn't. You can see a meter, but this is not Brownian motion. There's something unusual going on here. This is directed motion. And at first you think, well, they're little animals or something. They're not animals. These are just proteins. Completely inanimate system. So what we've got are actin filaments purified actually from a fruit fly. Okay, so the actin came from a fruit fly, and the myosin which we put on the surface here came from a rabbit. So you can take myosin from a rabbit, actin from a fruit fly, we just added ATP to the solution. That's all we've got in there, ATP and a little bit of magnesium. And then the actin filaments just start moving. And this actin had never seen a rabbit myosin the whole of its life, hadn't seen it for about 1 billion years or something. But in fact, actin is a very highly conserved protein. And it turns out you can take actin from virtually any organism and myosin from virtually any organism, and the two things will interact and do this motility assay. So it's quite a remarkable system in many ways. So we have a myosin on the surface, we've got actin filaments, and now to do the single molecule experiment, all we want to do is grab hold of one of these actin filaments and sort of hold on to its tail. So if we could get a plastic bead, dab it onto the back of one of these actin filaments, then we should be able to feel the myosin molecules tugging on the actin. We should be able to make that recording in time, looking at the fluctuations. So that's the idea behind the experiment. And in fact, it's slightly more complicated because if you want to record from a single myosin molecule rather than a whole bunch of them, you need to actually sort of present a single molecule up in the air. So we use what's called this sort of 3-bead geometry, where we have a bead here decorated, very sparsely decorated with myosin, then an actin filament held between the two particles in the optical trap, and then we can measure the position of those particles. We do that either with a 4-quadrant photodiode, or we do it with a camera system, but usually with a 4-quadrant photodiode. And then by looking at the fluctuations in position of these particles, well, in this example trace here, see that you get noise, and then you get interactions where the myosin has grabbed hold of the actin and pulled it. And let's just see that experiment now actually in action. So what you see, these are the 2 beads which are held in the optical trap. You can see some stuff moving around in the background because I'm moving the slide underneath. These are held in mid-solution in the optical tweezers. These are actually the 3rd beads which are being positioned underneath. Here's the 3rd bead that has myosin on. Watch this bead. Moves to the left. Now with the optical tweezers we can turn the actin round so it points the other way. And you remember that the actin filaments in your muscle have to go this way. They get pulled in one direction. So this actin filament, as it were, points. That would be the Z line. This would be the... Sorry. I'm really not good at this thing.
It was working.
It was working.
It was moving.
The other 2 graphics.
Oh, well, they're moving that. You see, if you leave them on their own, then they're happening. So you look, they get very shy. Okay, now we're on the right, but this one moves to the left. So the actin is pointing, as it were, in this direction. This would be the Z line, this would be the N line in the muscle fibre. Turn the actin round just to prove that it's doing what we think it is. So we rotate this. Now the actin's invisible, so this isn't a fluorescence image. So the actin's now pointing in this direction. So when we get the myosin molecules on here and we just touch it gently onto the actin filament, now this one starts moving again. And now by moving this optical tweezer out to the right, we pull the actin so it's held, so it's going to move to the right. Now the actin's under tension, so it's now held rigidly between the 2 beads. And now when the myosin molecules come down, now you'll see it move like a rigid body, like a dumbbell. It only moves by a very small amount. You're looking at movements of about less than 100 nanometers there. Because these beads are only 1 micron across, so they're only moving 1/10 of their diameter. And that particular recording produced data like this, where than seeing individual interactions, we've seen a long range version, as I say, of about 100, 200 nanometers. And that's because that particular bead had probably 5 or 10 myosins on that. So one could get on, another one could get on from behind and produce a large translational motion due to the action of lots of myosin molecules. We just dilute it down tenfold, 100-fold, and then we get down to the point where we get a single molecule interacting, and this now is what the single molecule interactions look like. And now it looks a little bit like that patch clamp record that I showed you, and indeed that simulation I showed you, where it just fluctuates between two states, and you can see these changes in noise, and also changes in position, and we can measure the deflection of the particle, which is produced as myosin binds and then pulls on the end. So we want to measure the amplitudes, and we want to measure those T on and the T off in order to get full all the information. And we do that essentially by, we have to, just one measurement will give you a very poor estimate because these times are stochastic in nature. And so the only way to get what the average time is to measure many hundreds of them. So you watch that one molecule, watch hundreds of interactions, you histogram them, and so it's histograms of T on and T off. That's the number of observations against time. And then you reconstruct an exponential behavior, both for either for T on or for T off. So that gives you your two rate constants, rate of binding, rate of unbinding. And then for the amplitudes, we need to measure the height, the distance that the particle moved when the myosin molecule grabbed hold of the actin and pulled on it. And the problem here is we can't measure it from just taking one interaction, because we don't know where the interaction started because of this background thermal noise. It could have started down here, it could have started up there. And so that contaminant noise and uncertainty in starting position again means we have to histogram the data. So we measure many hundreds of these interactions, plot them as a histogram, and it's the displacement of that, this is the number of observations, this will be the unitary amplitude, and it's the displacement of that, those unitary amplitudes from the rest position, which tells us the movement that's produced. And just, with this sort of averaging business, just to sort of, I don't know, just sort of get it in your mind a little bit. So if I measured all of your heights, okay, I'd have roughly a normal distribution or something in your heights. And then if I told you all to take your shoes off, and I measured your heights again, I'd see that same dumbbell, but it would be shifted by the average height of your heels. Now, there is something interesting actually in that. The reason I've used this silly analogy is that points to the power of single molecule experiments, because if you do that histogramming experiment, what you also find, if you take a room full of people and you measure the distribution of their heights, tell them to take their shoes off, measure the distribution of their heights again, you know what you find? You find not only is it shifted, it actually gets a little bit broader. And it gets a little bit broader because shorter people tend to wear higher heels than tall people. But what we all want to do is we're all desperately keen to get near the mean. Okay, so our distribution of heights when we're wearing our shoes is actually a tighter distribution than when we take our shoes off and get broader. And you can do that, so that's actually a single person experiment, that's sort of psychology versus sociology. So we can look at each one of you individually and try and discriminate what's determining your heel size. Anyway, so you could look at things and see, for instance, if this histogram is either broader, if it maybe has two shoulders, if there's one population which is producing a big movement and another population a small movement, all that kind of stuff comes out of this histogramming and the analysis of the individual records. Okay, now the other thing that comes out of these single molecule records is that, so we've got that idea that you might have heterogeneity in behavior between individual molecules or individual people, but you also get this, the ability to actually look much more closely at an individual record. And so here's one now stretched out in time, so we can look at it more closely. And so this is the movement of the particle. It's fluctuating with Brownian noise. The myosin molecule binds at this point and produces its power stroke. And then it sits at that new position, and then it detaches, and the thing goes back to its Brownian motion. And actually, you would never believe it, but I would tell you that there's a little extra movement in here. Now, you're not going to believe that, because there's no way you're going to believe that there's a little movement there because of the amplitude of the noise. Okay, I mean the noise. The amplitude of the noise here is way bigger than that possible movement. So how we now test whether, for instance, myosin produces one movement when it loses phosphate, and then another movement when it loses ADP, which is interesting because if the molecule loses the two products, when it loses phosphate it might do that, and when it loses ADP it might do an extra little movement. That's mechanistically very interesting. But how do we get that out of this data? Again, we go back to averaging, and now we do a process of what's called ensemble averaging. So ensemble averaging is where you take individual events, so I've drawn these schematically here. Here's a series of events. This is our hypothesis. So hypothetically, we think myosin binds and pulls, waits for a little while, loses its ADP, and then produces another little movement, very small movement here. And what we can do now is in the computer, we can synchronize all the events to the very start point, and we can synchronize all the events to the very end point, and then we can work back and forwards in time from the known start and end. And in fact, when we do that with that record I just showed you, when we did this for about 500 events, what we find is that at the beginning of the interaction, the actin filament moves by about 3 nanometers. But if we look at the end, the motion is now up to about 4.2 nanometers. And so something has happened between here and here. These things don't align perfectly. There's sort of a disconnect between the two. And that's because this loss of ADP produces a very small amount of movement. And you say, well, big deal, what does it matter? Phosphate produces some movement, ADP produces another movement. Well, that step, that two-step nature of the way that myosin works, it turns out is absolutely critical to myosin function. And I'll show you why that is for the next myosin we're going to look at. And that's this thing called, so all the experiments that we've talked about so far, myosins are a family of proteins, and you have 39 myosin genes. And so in different cells in your body, you've got all sorts of different looking molecules. They all have those little knobby heads which stick out. They're the bits that do the ATPase. And they have very different tails, as we would call them. So that's the motor, and this is the tail. And in muscle, that tail, remember, forms that very rigid, thick filament. But in other cells in your body, so in your brain, for instance, you have these things called myosin 5, and they're running around inside your neurons, carrying little vesicles of neurotransmitter. And so they have a tail region here which will bind specifically onto little vesicles, drag them around inside the cell and put them somewhere where they should be. And so these, as I say, these things are going on moving around in your brain at the moment. But they look rather different. They've got very different tails, but also the head is rather different. You know, this myosin 5 has a much longer neck region here. And that's interesting because the length of that neck, that looks like a lever arm. And so you would think this has a short lever. Short levers are good for producing high force, small movements. Long levers are good for producing long movements and small forces. And so this thing is adapted for producing much longer movements than your muscle myosin. Well, why do you want a myosin that produces a bigger movement and less force? And the reason is it's the two-headed nature of this thing. Let's move on here. I don't know whether this is going to work. Forget that. So if you have a long-necked molecule, okay, that's my muscle myosin. That just binds and pulls. There's one molecule on its own, and it's highly adapted to working in a team because you've got lots of molecules in your muscle, and they just want to get hold of actin, pull it, and then get out of the way. Pull on the actin. Every time the actin monomer comes past it, binds, pulls, and then lets go. And that's good if you work in a team because then you don't stop your neighbours from binding and pulling. But if you're working on your own, let's say you're a myosin 5 inside your brain cell, wanted to carry some cargo around, then does much better if this thing makes use of the fact it's got two heads and a long neck, so that it can actually step along the actin filament. And that means that one motor now, all on its own, imagine this is can now carry a bit of cargo, like a little autonomous machine marching away along the actin filaments in the cell, carrying one little vesicle with it. So these long-necked molecules are very well adapted for what's called processive movement, where they can move over very long distances, many microns, carrying a vesicle or whatever they're going to be carrying. And you need to do two things. One is have the long lever. The other is you need to tweak the kinetics, because you want to make sure that this trailhead has time to get onto the next actin binding site before the back head comes off, because if both heads detach at the same time, the protein will drift off, just diffuse away into the cytosol, and that's the end of your recessive writing. So you need to be absolutely sure that this head only comes off and the other head goes on. Now that, you say, well, that's easy. Well, you've just drawn a cartoon which says that's an easy thing to arrange, surely. But it isn't an easy thing to arrange because, of course, remember that biochemical events are completely stochastic. So what goes on in this head should be completely independent from what goes on in that catalytic site. So how do you couple the activities of two catalytic sites? How can you make that one talk to the other one? And the answer is they're coupled mechanically one to the other. So if we can make use of the fact we've got a mechanical coupling between the two catalytic sites, we might then be able to coordinate the activity so that it's only when this one binds that one can come off. So it really does march along one after the other. So we need to increase the coupling of between the two heads. And we can see, actually, when we do our optical trapping experiment, we can see that with this myosin 5, indeed, it does march along the actin fold. And it's taking one step after another. And so we and other people show that this thing does indeed work as a highly processive motor. So it does one molecule of myosin 5. You dilute it down, you get nothing. Bring it back up again, one molecule, and it does that. So one molecule looks like 1,000 myosin molecules from your muscle. It's a highly processive, independent motor. And the same thing was shown for another motor system called kinesin and microtubules, but they're also highly processive, and they take little steps, over 8 nanometers. These take great big steps of 36 nanometers.